Welcome to G Fun Facts Online. Imagine a car that is its own battery. Not a car with a heavy battery pack bolted underneath, but one where the floor, the roof, and the door panels are the source of its power. This isn't science fiction. This is the world of structural batteries, a technology that could completely rewrite the rules of electric vehicle design. For years, the story of the electric car has been one of compromise. The battery pack is the single heaviest component, a massive anchor that limits range, dictates the car's shape, and consumes energy just by being carried around. But a huge shift is happening. We're moving from a philosophy of simply carrying a battery to becoming the battery. This idea, called massless energy storage, merges the strength of advanced materials with the power of a rechargeable battery. The result is a vehicle that's lighter, more efficient, and offers incredible design freedom. Today, we're diving deep into the world of structural battery composites, exploring the science, the manufacturing, the incredible advantages, and the huge challenges that must be overcome before our cars and planes can truly become their own power sources. The idea for a structural battery didn't come from a single eureka moment. It's the result of decades of progress in two separate fields: composite materials and electrochemistry. We've known how batteries work for over 2 centuries, but the idea of making them structural is very new. It started with the use of materials like carbon fiber reinforced polymers, or CFRPs, in aerospace and supercars. Engineers loved carbon fiber for its amazing strength-to-weight ratio. The Boeing 787 Dreamliner, for example, uses a huge amount of it, making the plane 20% lighter than if it were built with aluminum. The real breakthrough came when researchers realized that the materials in composites and batteries had a lot in common. High-performance carbon fibers, the backbone of strong composites, are also pretty good at storing lithium ions, which is the key process in lithium-ion batteries. This sparked a revolutionary question. What if a material could do both jobs at the same time? Could it be both strong and store energy? Early research, led by scientists in Sweden and at Imperial College London, explored two main paths. The first and more straightforward approach is called an embedded or decoupled design. This involves taking thin, flexible, commercially available batteries and sandwiching them inside a composite structure. The battery becomes the core, and strong outer layers carry the mechanical loads. The second, and far more ambitious approach, is the monolithic structural battery. Here, the lines between structure and energy storage completely disappear. The carbon fibers themselves act as the negative electrode, or anode, while also providing the structural strength. The polymer resin that normally just holds the fibers together is re-engineered into a special structural battery electrolyte that can both transfer mechanical forces and transport ions. This journey from a wild idea to a working lab prototype has been incredibly fast. So let's look at how these things actually work. The world of structural batteries is really split into those two design philosophies: embedded and monolithic. The embedded approach is the one that's already on the road. A great example is Tesla's structural battery pack. Instead of putting their cylindrical battery cells into modules, and then putting those modules into a big heavy pack, Tesla bonds the individual cells together with metal sheets on the top and bottom. This creates a single, rigid, load-bearing structure that forms the floor of the car. It makes the whole chassis stiffer, improves handling, and because they got rid of all the extra packaging and modules, it led to a 10% weight reduction and a 14% range increase for the Model Y. It's a clever piece of engineering, but it's still essentially a battery pack that's been made to do a structural job. The true holy grail is the monolithic structural battery. This is where you get what scientists call a truly massless battery, because the mass of the energy storage system is the exact same as the mass of the structural part. A monolithic battery is built like a sandwich or a laminate, mirroring a conventional battery, but with a structural twist. First, you have the negative electrode, the anode. Instead of the usual graphite-coated copper foil, monolithic designs use high-strength carbon fibers. These fibers do two jobs at once. They provide the mechanical strength of the composite, and their graphitic structure can host lithium ions during charging. Next is the positive electrode, the cathode. This is often made by coating another layer of carbon fibers with an active material, like lithium iron phosphate. Here again, the carbon fibers act as a strong, lightweight current collector, replacing the traditional aluminum foil. Between these two electrode layers you have a separator. It's usually a thin, porous, electrically insulating fabric, often made of glass fiber, that prevents short circuits, just like in a regular battery. And now for the most innovative part, the structural battery electrolyte, or SBE. This is the special sauce. It's a multifunctional matrix that has to do two opposite things at once. It needs to be mechanically strong to transfer loads between the carbon fibers, like a solid resin. But it also needs to be ionically conductive to let lithium ions move between the electrodes, which is a job usually done by a liquid. The solution is often a phase-separated polymer system. Imagine a stiff, solid polymer skeleton that provides the structural integrity, intertwined with a network of tiny, interconnected pores filled with a liquid electrolyte that lets the ions flow. It's the best of both worlds. The charging and discharging process is a carefully choreographed dance. During charging, an external power source drives lithium ions out of the cathode, through the electrolyte, across the separator, and into the carbon fiber anode, where they're stored. During discharging, the process reverses. The lithium ions flow back to the cathode, releasing electrons that power the vehicle. But here's where it gets really complex. There's a phenomenon called chemomechanical coupling. When you charge the battery, lithium ions go into the carbon fibers, causing them to swell slightly. When you discharge it, the ions leave, and the fibers shrink. This constant swelling and shrinking creates internal stress in the material. If it's not managed properly, it can cause micro damage and degrade both the strength and the battery capacity over time. On the flip side, when the car corners or hits a bump, the mechanical forces can deform the composite, which can change the pathways for the ions, affecting battery performance. Understanding and engineering around this two-way street is one of the biggest challenges for scientists. So, how do you actually build one of these? The manufacturing processes are adapted from the world of high-tech composites. One common method is vacuum-assisted resin transfer molding, or VARTM. You lay down the dry fabrics for the anode, separator, and cathode into a mold, seal it all in a vacuum bag, suck out all the air, and then infuse the structural electrolyte resin. It's great for making large, complex parts like a car floor relatively cheaply. The challenge is making sure the resin flows everywhere without leaving any tiny air bubbles, which would be disastrous for both strength and battery function. For the highest performance parts, you use an autoclave. This is like a high-tech pressure cooker. The composite material is put inside and then subjected to intense pressure and heat. This squeezes out any imperfections and creates an incredibly strong, dense, and reliable part. It's the gold standard for aerospace, but it's very expensive, slow, and can't make parts that are bigger than the autoclave itself. A newer, more flexible approach is 3D printing. This allows for incredibly complex and optimized shapes that are impossible with other methods. Researchers are exploring printing with continuous carbon fibers that are already coated in a solid polymer electrolyte, essentially building up a structure with millions of microbatteries integrated throughout. While 3D printing is amazing for prototypes, scaling it for mass production is still a huge hurdle. Now for the exciting part, the rewards. If we can perfect this technology, the benefits are transformative. The biggest advantage is radical weight reduction. In a normal EV, the battery is just dead weight. It's called parasitic mass. A typical battery pack can weigh hundreds of kilograms, which means you need a heavier frame, bigger motors, and stronger brakes just to support it. Structural batteries eliminate this parasitic mass. The car's floor is no longer just a floor, it's also the battery. You eliminate the heavy battery casing and redundant reinforcements. Researchers estimate this could reduce a vehicle's overall weight by as much as 50%. This creates a virtuous cycle. A lighter car needs less energy to move, which means you can use a smaller, lighter battery for the same range. A smaller battery means lighter suspension and brakes, saving even more weight and making the car even more efficient. The direct result of this weight loss is a massive increase in range and efficiency. It's basic physics. A lighter object requires less energy to move. A 10% reduction in an EV's weight can improve its range by about 7 to 10%. Apply this to structural batteries, and the numbers become incredible. Research from Chalmers University in Sweden suggests that an EV with structural batteries could see its driving range increase by as much as 70% on a single charge. This isn't just a small improvement, it's a leap that could completely eliminate range anxiety. Beyond efficiency, this technology unleashes automotive designers. For years, cars have been designed around big, bulky engines, or, more recently, large, flat skateboard battery packs. Structural batteries shatter these constraints. With energy storage distributed throughout the car's structure, engineers are free to create more spacious interiors, lower seating positions, and radical new vehicle shapes that are more aerodynamic and efficient. The vehicle's entire body becomes a potential power source. This also improves performance. Making the battery an integral part of the chassis makes the whole car much stiffer and stronger, which improves handling, ride quality, and crash safety. And there are potential safety benefits. Instead of having all your energy concentrated in one giant pack, distributing it throughout the structure could reduce the risk of a single-point failure, leading to a catastrophic fire. And many of these designs use safer solid or semi-solid electrolytes. But of course, the road to this revolution is full of roadblocks. The biggest challenge is the fundamental tug-of-war between energy and strength. The properties that make a good battery are often the opposite of what makes a strong structure. For example, to store a lot of energy, you want your electrodes to be porous with a lot of surface area. But porosity is the enemy of mechanical strength. Current prototypes have a lower energy density than traditional batteries. The weight savings make up for it, but the goal is to close that gap. Similarly, the electrolyte needs to be a great ion conductor, which is best done with a liquid, but also a stiff, solid-like material to transfer mechanical loads. Finding a single material that does both perfectly is the key challenge. Another hurdle is the interface between the carbon fibers and the electrolyte matrix. The constant swelling and shrinking of the fibers during charging and discharging can cause them to separate from the matrix, creating microcracks. This weakens the structure and kills the battery's performance. Then there's the manufacturing maze. Scaling up from small lab samples to large, reliable car parts is a huge challenge. Current high-quality methods are very expensive, with some estimates putting a structural battery system at 2.5 to 3.5 times the cost of a conventional setup. Quality control is also a nightmare. A single tiny flaw could compromise not just the strength of a car door, but also its ability to hold a charge. And finally, we have to consider the safety and life cycle equation. This is perhaps the biggest practical problem. What happens if a door panel that is also a battery gets dented in a minor accident? Does it still work safely? And the biggest question of all, what happens when the battery reaches the end of its life? If your car's floor is the battery, and it degrades after 10 years, do you have to throw away the entire car? This prospect of forced obsolescence is a major economic and environmental concern that has to be solved. We need entirely new strategies for repair and new recycling processes for these incredibly complex materials. So what does the future hold? The path forward is all about innovation. Researchers are working on new materials, like higher energy density cathodes and advanced solid-state electrolytes that are safer and more conductive. They are also exploring other chemistries, like sodium ion, which would be cheaper and more sustainable than lithium. Artificial intelligence is playing a huge role here. I can analyze massive datasets to predict the properties of new materials, dramatically speeding up the discovery process. And the transition from the lab to the road is already happening. Tesla's structural pack is a first step. Volvo is planning to use the battery pack as a structural floor. Hyundai and Kia have filed patents for similar ideas. And research leaders like Chalmers University are consistently pushing the boundaries, getting ever closer to that goal of a 70% range increase. To become mainstream, costs must come down, and manufacturing must be automated. We will also need a whole new ecosystem for testing, certification, and, crucially, repair and recycling. Structural batteries are more than just a better battery. They are a complete reimagining of what a vehicle can be. They offer a clear path to lighter, more efficient, longer-range electric vehicles. The road is long, and the challenges are real, but the potential reward is so great that it has ignited a global race to perfect this technology. The vehicles of the future might not look all that different, but their very essence, their very skeletons, will have changed. They will be a working, integrated system of structure and power, bringing a level of efficiency and design freedom that was once pure science fiction. The silent revolution is here, and it's being built, literally, into the fabric of our future. Thanks for listening to G Fun Facts Online.